So we're really living in this connected world now, aren't we? Data just popping up absolutely everywhere.
Oh, completely. From the massive cloud data centers all the way down to like a single sensor embedded in a traffic light.
Right.
Or even your power outlet.
Right. And trying to manage computation and networking across that whole span, cloud, edge, IoT devices, that's where the really tough challenges are today.
It's definitely not just about spinning up virtual machines anymore. I mean, when you get into these high-stakes situations.
Yeah, like public safety.
Exactly. Public safety, autonomous cars, managing energy grids. You need an orchestration layer that's, incredibly fast.
And aware of everything changing.
Aware of network hiccups, constantly tuning itself for latency or power saving, whatever the goal is. It needs to be smart.
And that really brings us right to the heart of this deep dive, CODECO, which is this cutting-edge framework designed precisely for that job.
Right. It's a containerized application orchestration framework built for this complex cloud edge world.
So, our mission today, for you listening, is basically to give you the fast track on CODECO. We're going to unpack the plans for its final deployment and demonstration.
Yeah, we've got 6 really innovative use cases. Pilots they call P1 through P6, and they show exactly how this framework juggles compute and network resources.
So we're moving past the theory, looking at actual deployments, smart cities, factory floors, power grids.
Real-world stuff, showing how it adapts in real time, how it manages efficiency, resilience.
Okay, let's unpack this. So before we jump into those really cool pilots, we probably need to get a handle on the framework itself. What's CODECO actually doing?
Fundamentally, its job is optimizing those key metrics: latency, power use, how fresh the data is across all these different environments. Could be a single edge cluster, could be a whole federation of them.
And it serves 2 main groups of people, right? The developers building the apps?
Yep, that's user DEV, and then the people managing the apps once they're running user MGT.
Got it. And how does it pull this off? What are the building blocks?
It uses 5 highly specialized components. Think of them as layers sitting on top of standard stuff like Kubernetes, K8s.
Okay, the big 5. Let's walk through them. Where do you start getting things running?
Exactly. That's ACM, Advanced Configuration and Management. You can think of this as the initial deployment brain.
Okay.
It automates the setup and configuration of your application stack across that whole cloud edge IoT continuum, what they call CEI.
And it's smart about it.
Yeah, that's the key. It considers the compute needs, the network setup, even where the data lives from the get-go.
Right. So ACM sets the stage correctly. But things change, don't they? A node gets overloaded, the user moves, you need dynamic adjustments. That brings us to the next piece, the really dynamic one.
Yes, that would be SWM, scheduling and workload migration. This is the core intelligence deciding where something should run moment to moment.
So it's a scheduler.
It is, but it's a novel scheduler for K8s. It goes way beyond just checking if a node has enough CPU. It looks at data location, network quality, the actual computation load to find the, quote, best match in real time.
But wait, standard K8 schedulers, they handle placing things initially, right? What's the extra complexity SWM is dealing with here?
The really crucial part is its ability to do application workload migration, specifically what they call SWM4 functionality.
Migration, meaning moving something that's already running.
Exactly. SWM can take a running application and its current state, keep the service going, and physically move it to a completely different node, maybe even in a different location.
Without anyone clicking a button.
Totally autonomous, based on some trigger. That's a really hard problem in distributed systems, and it's absolutely fundamental for genuine resilience.
I see. Okay, so ACM gets the job started right, and SWM makes sure it stays right, adapting to whatever happens. Makes sense. What about knowing what's going on? How does CODECO get its situational awareness?
That takes 3 different components working in concert. First up is PDLC, privacy-preserving decentralized learning.
Decentralized learning, because you can't just monitor everything centrally if it's spread out.
Precisely, especially in a federated setup. So PDLC gives you that context awareness. It estimates the overall system stability, that's PDLC-1, across all those distributed nodes. And crucially, it provides an aggregated cost view, PDLC-2.
Cost view, like energy cost, latency cost.
Both, potentially.
Yeah.
It gives SWM the info it needs to make those smart, cost-aware decisions. Like, should I move this workload to save power or to reduce latency?
Gotcha. So PDLC is kind of the system's eyes and ears and maybe its gut feeling about overall health.
That's a good way to put it. Then, laser-focused on connectivity, you have NetNapp, network management, and adaptation.
Just the network pipes.
Yep, it delivers network awareness, that's NetMail1, and makes sure all different application pods can talk to each other securely, which isn't trivial, when you've got edge clusters maybe managed by different organizations.
Right, security and just basic connectivity across boundaries. Okay, and the last piece, dedicated to the data itself.
That's the MDM, Metadata Manager. This one is really interesting because it treats data as a resource.
Data as a resource, how so?
It provides metrics about the quality of the data flowing through the system. And the absolute star metric here is age of information, AOI.
AOI, data freshness.
Exactly. How old is this piece of data right now? MDM tracks that, along with things like compliance rules and data portability levels.
Wow, okay. That distinction feels really important. You're not just watching CPU load anymore. You're actively asking, is the data I'm using actually relevant right now?
Precisely. Think about it if your autonomous vehicle safety system is crunching numbers based on sensor data that's 10 seconds old.
Doesn't matter how fast the CPU is. The decision could be dangerously wrong.
Exactly. The system might as well be offline. AOI is critical.
Okay, now I see how these 5 pieces, ACM, SWM, PDLC, NetMA, MDM, fit together. It's a complex dance.
It really is, each playing a vital role.
Right. Here's where it gets really interesting. Let's dive into those pilots. These concrete examples really bring it to life. Starting with P1, the smart traffic monitoring and getting in. High stakes, mobility.
Yep, this one's a classic edge computing challenge, handling massive data loads locally. The goal is better traffic flow, safer pedestrians. They're using LiDARs, thermal cameras right there at the intersection.
The far edge.
The far edge. And these sensors, they generate huge amounts of point cloud data.
Yeah.
Needs local, real-time processing.
So what happens during rush hour? That data volume must just explode.
Yeah.
How does CODECO keep up? How does it guarantee that real-time analysis doesn't just fall behind?
It uses that SWM4 migration capability we talked about, triggered by a metric from MDM. They set a threshold for, say, data volume on a processing node.
Okay.
If heavy traffic makes the incoming data exceed that threshold, meaning the node can't keep up, boom, CODECO gets triggered.
And SWM steps in.
Instantly. SWM identifies a less busy K8s worker node nearby, could be in the same cluster, intra-cluster, or even a different one, inter-cluster, and offloads those point cloud processing tasks.
Seamlessly moving the work.
Right. And they have a hard target. They want to see at least a 5% increase in the average number of frames processed per second per node, thanks to CODECO's intervention. Measurable improvement.
That's fascinating. Adaptation based purely on the sort of kinetic load of the traffic itself. Now, P2 takes it up a notch. The vehicular digital twin in Barcelona, this involves protecting vulnerable road users, VRUs.
Pedestrians, cyclists.
Right. And this brings that age of information metric front and center because safety here means ultra-low latency is non-negotiable.
Oh, the requirements for this pilot are incredibly strict, almost demanding. The latency target, less than 20 milliseconds, round trip, cloud to the vehicle's onboard unit or the VRU's phone, and back again.
20 milliseconds. Wow.
And the AOI targets, the data freshness, maybe even tougher. Average AOI has to stay below 70 milliseconds. The peak AOI can't exceed 200 milliseconds.
If the data gets older than that.
The digital twin representing that pedestrian is out of date. It becomes a safety risk, not a safety feature.
And I can see how dynamic this must be. A pedestrian with a smartphone walking down the street, their best connection point, their optimal edge node is constantly changing.
Every few seconds, potentially. That's the real-time problem SWM has to solve here. If that VRU moves and their latency starts creeping up past the limit,
SWM notices.
SWM notices, thanks to the monitoring, it then dynamically reschedules and migrates the critical services, maybe the module processing the V2X safety protocols, or aggregating the digital twin data, moves it to a closer edge node.
Like one of those powerful NVIDIA Jetson Orin devices you mentioned?
Could be, yeah. Something closer with the right capacity. The whole point is to keep that information stream fresh, hitting those tough AOI targets despite people physically moving around.
Okay, so we've seen CODECO handle speed and location dynamics. Let's pivot slightly. What about resource optimization, specifically energy? That takes us to P4, right? Demand-side management at the UPM campuses.
Yeah, this one's all about making buildings greener. Using active demand response, integrating renewables, solar panels, battery storage systems, BESS, even EV chargers.
And the goal is pretty ambitious.
Definitely. They're targeting a 5 to 10% cut in energy consumption and CO2 emissions. Plus, they need to be able to roll out new energy-saving functions really quickly under a minute deployment time.
This sounds like a textbook case for that synergy you described earlier. PDLC providing insights, SWM acting on them.
Exactly right. This pilot really leans on PDLC's strength,
Yeah.
delivering those dynamic energy forecasts based on data collected across the campuses.
So PDLC figures out, hey, solar power is cheap right now, or demand is peaking.
Precisely. And SWM takes that forecast, that aggregated cost view, and uses it to make smart, energy-aware scheduling decisions.
So if energy prices spike, or maybe the solar panels are generating tons of free power,
SWM dynamically shifts the computing tasks. Maybe it moves non-critical workloads to run when power is cheapest or greenest, distributing the load intelligently across the 3 different UPM campuses.
very cool. And that same kind of adaptive thinking extends right onto the factory floor with P5, the wireless AGV control pilot. AGVs, automated guided vehicles.
Acting as Kubernetes worker nodes themselves, which is pretty clever.
Right, so the challenge here is resilience. Factories are noisy places, wireless can be flaky.
Exactly. Industrial environments are tough. Wireless signals get interfered with, batteries run down, but the control systems running on the AGVs, things like SLAM for mapping and navigation.
Simultaneous localization and mapping.
Right. That microservice absolutely cannot fail just because an AGV's battery is dying or it hits a wireless dead spot. The whole production line could stop.
Okay, so walk me through it. An AGV system detects, battery level critical.
Yeah.
What does CODECO do?
That low battery warning or maybe a predicted battery failure for monitoring acts as the trigger. SWM automatically scans for another suitable AGV nearby, one that's charged and available.
Well then?
And then it initiates that SWM4 workload migration. It seamlessly lifts the running microservices like SLAM off the failing AGV and moves them onto the healthy one.
But that's stateful migration, isn't it? SLAM needs its current map, its location data. You can't just restart it. How do they move that state reliably, especially over potentially spotty factory Wi-Fi?
That's the technical magic. They're using standard Kubernetes features, specifically persistent volume claims or PVCs.
Okay.
This allows the critical state data, the current map, the vehicle's position estimate, to be stored in a way that it can be quickly shared and accessed by the new AGV worker node when the migration happens.
So the new AGV picks up right where the old one left off.
Exactly. And by making this migration fast and reliable, they're actually aiming to reduce task completion latency by 20%, because the decentralized control is more responsive than waiting for a central server. Plus, they expect fewer collisions.
Wow, okay. We've covered traffic, pedestrians, energy, robots. Let's tackle the trickiest physical environment, P6. The crownstone deployment in smart buildings. This feels like the ultimate far edge.
It really is.
Yeah.
Because the crownstone devices themselves, these are smart modules, basically, sitting inside power outlets.
Right.
They are non-IP devices. They don't speak the language of the internet or typical networks.
How on earth do you orchestrate them using Kubernetes and CODECO, which are built around IP networking?
This required a really significant innovation within the CODECO deployment model. The solution is something called virtual kubelets, VKs.
Virtual qubits. Okay, break that down. How does that work?
So the VKs don't run on the crownstones themselves. They run on intermediate hardware called crownstone hubs.
Got it.
Each VK acts as a proxy, a kind of virtual stand-in for one or more of those non-IP crownstone nodes downstream.
So it makes the dumb power outlet look like a smart K8's worker node to the rest of the system?
Precisely. This virtual representation lets CODECO, using ACM for the deployment part, orchestrate pushing tiny microapps directly onto those power outlets. It effectively brings this previously isolated physical infrastructure right into the main edge management system.
That's brilliant and bridges the physical hardware gap. And the triggers for redeploying things here seem really interesting too. It's not just CPU load or battery anymore.
No, much more nuanced. They have 2 main complex triggers defined. The first one is topology-based.
Meaning?
If someone physically installs a new crownstone outlet in the building, CODECO automatically detects this change in the physical layout.
And then?
It expands the virtual cluster representation, and ACM figures out the best hub to host the new virtual kubelet for that new outlet. It's self-configuring, self-expanding infrastructure.
Okay, that's automation based on physical changes. What's the second trigger? Something about people in the building.
Exactly. It's occupancy-based. This monitors the health of the Bluetooth Low Energy Network, the BLE network that the crownstones use to communicate locally.
And people affect Bluetooth.
Oh, definitely. How many people are around, how many phones are active, even physical obstructions. It all impacts BLE, signal strength, packet loss, things like that.
Okay.
So when those BLE network statistics monitored by NetMag go outside acceptable thresholds,
CODECO steps in again.
right, it triggers redeployment actions. Maybe it adjusts the power levels of certain microapps running on the outlets, or removes computationally expensive ones if the network is struggling, to actively optimize the BLE performance for the current number of users.
And the goal is just making it easier to manage these smart buildings.
Yeah, the key KPI is measuring the reduction in effort needed to deploy and expand these systems compared to doing it all manually. It's about operational efficiency.
Man, when you lay out all 6 pilots like that, it really shows the incredible range of this framework. We went from managing, high-speed traffic data
To ensuring data freshness for pedestrian safety,
to balancing green energy loads,
making factory robots more resilient.
and even optimizing Bluetooth in an office based on how many people are having coffee.
And the technical reports back this up. There's a core set of CODECO functionalities. ACM1 for installation, SWM1, 2, and 3 for different kinds of placement and deployment, NETMA1 for network awareness. These are used across all 6 pilots. They're foundational. Then the really specialized stuff, like the SWM4 migration or MDM's Age of Information tracking, gets layered on top only when the specific problem demands it. It's modular.
So this report we've been digging into, it's really setting the table for the final proof, isn't it? What's the immediate next step for CODECO?
Yeah, the focus shifts entirely now to what they call Task 5.4, the demonstration plan. It's a formal process.
Which involves?
Detailed planning for each demo, prepping the sites and equipment, actually running the demonstrations, and then disseminating and evaluating the results.
So showtime, basically.
Pretty much. The very next step is running these full-scale demonstrations to really hammer on the framework, validate its performance, its scalability, especially in tricky multi-cluster setups, and prove these adaptations work reliably under real pressure.
Okay. So stepping back, what does this all mean? When you see a framework that can autonomously shift workloads around based on energy prices or traffic jams, or even, like you said, the faint signals of a Bluetooth network, that feels like more than just optimization.
It does.
What new possibilities does this open up? Are we talking about, truly adaptive cities, systems that heal themselves?
I think that's exactly where it points. It fundamentally changes the engineering approach, doesn't it? Instead of designing for the absolute worst-case scenario and throwing hardware at the problem.
Over-provisioning everything.
Right. You can start to rely on the system itself to constantly find the best operating point, reacting intelligently to the real world in real time. It's a shift towards self-managing, self-optimizing critical infrastructure.
It implies a future where the systems running our cities, our factories, our energy grids are far more resilient and efficient because they can constantly adapt.
That's the promise, absolutely.
So if you're listening and you want to dig deeper, maybe into the economics of that decentralized learning with PDLC, or the nitty-gritty of calculating age of information, or how those virtual kubelets are really bridging the gap to the far edge, hopefully, you now have a solid framework, pun intended, to keep exploring.
Yeah, we really encourage you to think about those complex interactions, those triggers and migrations we discussed today. There's a lot there.
Until the next deep dive, happy exploring.